So my name is Marya Hussein, and this summer I conducted research at the University of the Virgin Islands with my mentor, Dr. Dario Carbone, and the title of our research was Searching for Radio Transient Sources. So what are radio transients? We define radio transients as sources that can only be detected for a limited amount of time in the radio band. We detect them by looking at images that appear, disappear, become dimmer or brighter in our images. We use instruments with good resolution, good sensitivity, example LOFAR and VLA, which contains many radio antennas that work well together. As you can see, LOFAR is the image down below and VLA is the one above. And they are two different instruments because the VLA has dishes, whereas the LOFAR does not. And LOFAR has many advantages, which include it is much cheaper to build, and we can observe two different sources at the same exact time. And also, you can use this configuration LOFAR for radio waves and low frequency. Given that VLA is the most powerful instrument in the world, it does not operate at this frequency, so that is why the VLA cannot have the same style as LOFAR. I just introduced what radio transients are, and now I will introduce why we study them. So why is it interesting to study radio transients, or why this project? So radio transients in general, they typically include some of the most energetic events in the universe. Calculating the transient rate is an important tool to better understand what is causing some of these unknown events. And because they are important, I search for new transient sources and measure the transient rate from my data. I have used data collected with the instrument LOFAR, which is at low radio frequency. And I looked at 40 images from two different fields, two different regions of the sky. So I collected data on from multiple parts of the sky. And given the images, I then examined the brightness of 8 different sources. These are two examples of images that I looked at, and they are from two different fields. I monitored the flux of these sources, and I have chosen these 8 because they are brightest and they are scattered rather than being clustered together. I have also measured the field of view of these images, and the field of view, which is on the bottom left, which it is 28.5 degrees squared. And it is also the same for all of the images. As an example, I am showing the light curves of the source highlight above. So the one on the light curve on the right is for this source, and the light curve on the left is for all of the sources in this image. So we have checked that these light curves are consistent with the horizontal line, meaning constant source. We have done the linear fit-in for all the sources, and all of the sources were constant with a constant source. In the image on the left, different sources have different colors. So if you want to follow a source, you follow the same color. So you can note that there's data points that are very much below the others, and that is because the source is fading, but we think that the data point is because the source is fading, but we think that the data point is coming from an image that was not good. And we can say it because we've seen the same behavior for all of these sources in the same exact image. So none of these sources were transient. And so what we did was set an upper limit for the transient surface density. We have done it using the method described in Carbone et al. 2016. And this method implies that limit on transient surface density is inversely proportional to to the number of images. Meaning if I have more if I have more images, I have better results. So when we apply this method, it is the whole data set we obtain on the bottom right, and it is lower than 0.003 degrees to the -2 for sources brighter than 1 Janskis. I have all of these other data points because I'm doing the calculation over and over again, and every time I start again, I am eliminating the noisiest image. And the reason we discard the noisiest is because it is the one limiting our sensitivity. So we perform the calculation and discard the noisiest image using one image less. Therefore, my new data point would have moved to the left because I removed the noisiest image, resulting in a less noisier image. And it is moving up because I have one image less. And the transient surface density, since it is inversely proportional to the number of images, my limits will become bigger. And thank you. That concludes my presentation.